Hello, everyone. I'm Dr. Silvia Del Din, and I am a Newcastle University Academic Track Fellow. I'm the WP2 Deputy Academic Leader, and I'm here on behalf of the Academic Leader of WP2, Professor Claudia Marzà, who unfortunately couldn't be here today. Welcome, everyone, to this fourth webinar. And just a few words about Mobilise, if you haven't already joined the other webinars. Mobilise is a multi-million project, and it's funded from the European Union IMI2 initiative. It's a 5-year project was started in 2019, and the goal is connecting digital mobility assessment to clinical outcomes for regulatory and clinical endorsement. The consortium is very large. It includes 34 partners, including public institutions, obviously academia, pharmaceutical company, small and medium enterprises, and technology partners. Mobilise consortium is co-led by Professor René Rochester from Newcastle University and Dr. Robin Rubenov from Novartis. So really the aim and the scope of WP2, the technical validation work package, is really trying to get valid metrics and valid tools to measure mobility performance. So Mobilise is proposing a device-agnostic approach to quantify mobility disability using digital mobility outcomes during a 7-day period of unsupervised monitoring. So we're collecting data in the real world to get mobility performance. We are collecting data with devices, and we want to really quantify the minimum requirement for these devices. And then we want to quantify through validated algorithms, validated digital mobility outcomes that can then be linked to clinical endpoints. All of this and this concept has been shown, and you can find it on our YouTube channel, and it's the first session of this webinar series. In the second session, you have been able to, or you will be able to see, the description of the experimental tool. So how are we collecting data from the device bench testing to the in-lab observation to the real-world observation, and which analytics and which tools we have utilized. In session 3, we describe the protocol and the patient journey. And as you can see, again, the recording of the webinar 3 is available on our YouTube channel. So today, the webinar is really focused on the tools for data transfer and analysis. So we have used tools, we have collected data, and now what are we going to do with it? So in the first talk, Dr. Hugo Hayden will talk about the science platform, which is the platform that we utilize to really manage and transfer our data and for the analysis of the data. The analysis of the data will be actually be presented by Cameron Kirk, and he will show how we have utilized this science for doing this. Dr. Luca Palmerini from University of Bologna will then describe how we have standardized the data. So we have collected a lot of data, and how have we standardized in-lab and out-of-lab data files. And Professor Brian Coffin from UCD will also talk about the data sharing policies that Mobilise is really discussing and will then implement. And then lastly, myself, Dr. Sarah Koch, will present the statistical analysis plan. So what and how are we going to analyze the technical validation study data? We want also to thank Anne-Lee Carsen, who cannot be here today, but she has helped, obviously, with this piece of presentation and this piece of work. Again, a disclaimer, obviously, what I have said and what all the speakers today will present is solely our opinion, and it's not the opinion of the funders. And now, without further ado, I'm going to pass the stage to Dr. Hugo Hayden that will talk about the eScience Central Platform.
My name is Hugo Hayden, and I'm one of the main architects for the data management platform of Mobilise. I'm based in computing science in Newcastle, and I've been responsible for creating the infrastructure that captures and processes data collected by Mobilise. So, as you can imagine, collecting data from the thousands of participants across the EU needs quite a large level of coordination and organisation. These are statistics from the CVS data collection as of March this year, 2022. There have been about 3,000 participants who have been registered with the platform in some ways. Not all of those will have progressed, but that number is rising all the time. There are sort of 31,000 individual documents have been submitted so far. And these are the movement data files that have been collected from the activity monitors, various videos, notes, that sort of thing. And about 83,000 forms submitted. And these are things like standard clinical scales, height, weight measurements, various things like that that have been collected from forms. This is just on the CVS before we even started to collect and process data. And to put that into context, the technical validation study, the TVS, which has had a lot less participants, so a few hundred, that's been benchmarking all the algorithms, and that's now got over 3.5 million different objects and pieces of information on it as a result from benchmarking the algorithms. This will also apply to the CVS as we start processing the data, so the amount of information here will only grow and grow significantly over time. Second part of that has been to collect all of the bits of code together to process the data. So we've been coordinating about 50 developers around the project, submitting code to the platform to analyze movement data. And we've got about 40 odd different algorithms and pieces of code that have been packaged together. And we've run that tens, probably now hundreds of thousands of times through workflows. So there's a lot of coordination needed to actually gather this data together, gather the code together and run it at scale. Now, from my perspective, one of the biggest challenges so far has been actually packaging this code together. As I say, there's been many different developers around the EU contributing code. Most of that's been written in MATLAB, of a variety of versions with different toolboxes. Some of it's in Python, again, with different libraries and toolboxes and things. It's not really feasible to rewrite all of this for Mobilise, partly because of the effort it would take, and also because some of this stuff has been published and the original authors aren't around anymore to actually help us with that. So what we've done is try to package everything into these containers using something called Docker. And what that does is package all the code, libraries that you need to run it into a single container that you can then run on a computer somewhere. So we have created a lot of containers for all the various bits of code that Mobilise produced and actually stored them in an archive, which means that we can then bring those to bear on the data as we collect it. Now, we run these containers in the platform, the data management platform that Mobilise uses, which is based on something called eScience Central that I'll cover later on. The benefit of using these containers is they can all coexist in the same place. So we can have some bits of code written in one version of MATLAB, some in another, that on their own might not work together, but can actually run in the same environment because we've isolated everything together. So we connect MATLAB, Python, various bits of code together into a single sort of runtime. Another benefit of that is that once you package these containers, they don't change anymore. So from an auditing and regulatory perspective, we know what bit of code we're running at any given time on a piece of data. It also means that we can build and test these containers as part of the technical validation study. And once that we're happy with those and found the best ones, we can move those straight into the clinical validation study and be absolutely sure that we're running the same code between the two sets of studies. So there are many different views of data flowing through Mobilise. This is as simple as I can create one, really. We have files uploaded from various places. So the accelerometers are strapped to people. Data is collected and passed to Roberts, who upload it straight into our platform. We have some data files and forms captured by ERT, who are now called Clario. And they have an application, I think, called StudyWorks that people use to fill in various forms, clinical scales, as they meet patients. And we've also created some of our own forms to capture data that isn't supported by ERT and Clario. This all gets pulled together into our data management platform. Again, I'll talk about that later. And it's stored and associated with participants or patients. So a patient record gets created. They have all these files associated with them, all the form data, all the documents, and all of the DMOs that have been calculated by the code that people have uploaded. This is all stored together and curated for each patient. And then periodically that's pulled into a data warehouse. And that is what we use to then generate reports, for the regulatory submission and for project management and the rest of it. So talked about eScience Central, the platform everything's built upon. So we've used this as a platform, the foundation for Mobilise. For several reasons, really. Firstly, it's mature. It's been around for quite a while now. We've used it very widely in Newcastle. It's supported. It's open source, and we understand it completely. So we know exactly what we're doing with this. Its big strengths have been storing and processing data, which is fairly fundamental to Mobilise. We support a lot of different algorithms, and by using Docker, we can support code written in pretty much any language. It scales nicely, so we've definitely scaled it to fairly significant levels. We've done things like process all the biobank data using it. So we know that we can actually run lots of data through this at good scale. And also, we support external systems pushing data into the system via various APIs. And that's what we've used to capture data from Roberts and also from the web forms that we've created. So I'm just going to show you quickly what the platform looks like and how you use it. So if I drop into that now. So this is the basic eScience Central platform. It's based around data, workflows, studies, and sort of organizing information. So at its very simplest level, there are files of data that you store. So each project or study gets its own folder, and you get your own folder as well. So any file can be uploaded much like you would in a Windows Explorer. You can drag data in and store it in here. The difference is that this is backed by cloud storage. So there's no effective limit to the amount of data you can store in this system. So you can keep adding and adding to it, and it will just grow automatically. So if I look at one of these files, every time you create a file, you get a new version of it. So this is a single version. We also have information about who uploaded it and when, and we can download the file as well for viewing. So by default, you can store your own private files, and each project gets a shared folder. And it's these shared folders that are used to store the data from patients and all the results of the workflows. Okay, so if I look at a quick workflow now, workflows are a way of graphically drawing out how you want to process data. So if I look at one of these, this is a simple workflow that processes a file from one of the TVS studies. And what happens is that we create these workflow blocks that you can drag onto the workflow and connect together. Each one of those can be written in a different language or by a different contributor. So for Mobilise, these are all the blocks that we've created so far to support the project. So as you can see, there are quite a few different algorithms and bits of code that Mobilise has created. If I just run a quick workflow now to show you how it works. So I create a new workflow, import some data. So import some data. And what I'll do there is create a report summarizing that and export the results. So then I run that. And what happens then is that gets sent to one of the machines running in the Amazon cloud, which will actually do that processing. So I'll come back to that in a minute when it's finished. Now, the idea of these workflows is it will define a workflow that runs on a single file in a project, like a single movement file or a single day's worth of data. Once we've got that running for one file, we can then run it across all of the files in the study. So, we would create a simple workflow that just focuses on a single file for a participant. Then once that runs, we then have another workflow that we apply to a whole study. The benefit of that is that we can run all of those things in parallel, and so it becomes much quicker than actually going through it file by file. And also you can run it, leave it running, and then come back later to see how it's progressing. So you're not tied to actually looking at it all the time. So if I go back to that file I ran earlier, it's now finished generating a report for the data. Again, the results are here. And if I have a look at that, that has basically just created a fairly large report summarizing everything that was in that data file. So once it's running at scale, we can run this hundreds of times in parallel over all the files in the project automatically, which has made it much easier to do the benchmarking. And also, as we collect data from the CVS study, we can process that much quicker than we would be able to do on a single machine. So to summarize, before Cameron takes over, WP2 uses an existing platform to process data. That saved us a lot of time in that it's a system that already exists, scalable, and has a lot of features on it that we wouldn't be able to replicate in a reasonable amount of time otherwise. We standardized and packaged a lot of algorithms in containers. So it means that people can use the runtimes that they're happy with. Also gives us a degree of portability between the TVS and CVS studies. Data is uploaded to studies associated with patients. So we try to automate as much of this to reduce errors. And we use these workflows to graphically define what we want to do with the data. So it's obviously a complex process to do all the benchmarking and sort of work out which algorithm is best. But the platform underneath all that does a lot of the kind of automation heavy lifting, which means that people can focus just on the results and not on coordinating all of the sort of various bits and pieces underneath all that. So if I hand over to Cameron now to carry on to talk about the how the platform actually processes movement data from Mobilise. Thank you.
So my name is Cameron Kirk, and I'm a second-year PhD student from Newcastle University. And today I'll be telling you how eScience Central works for data analysis in the Mobilise technical validation. So in short, a major goal of the technical validation study was to rank and identify the single best algorithm combination for each block of the digital mobility outcome pipeline. So firstly, a reminder of the DMO pipeline and the algorithms that were compared within each block. The input data for the pipeline is from the inertial measurement units within the McRoberts device. From the IMU data, we first applied 8 algorithms for gate sequence detection. 17 algorithms were assessed for step detection, before 3 left-right step detection algorithms, and 1 algorithm was applied for turning detection. And then we applied 20 for cadence estimation and subsequently evaluated 19 step length estimation algorithms, which then enabled estimation of real-world walking speed, which is the ratio of step length to step duration. Although other blocks, such as pre-process, exist in the DMO pipeline, the algorithms I mentioned are the only ones which were compared and evaluated on the eScience Central platform. Details of each block of the entire pipeline have been covered in previous webinars, and how we statistically compared their performance will be covered later today. First, I'll be sharing how we use the eScience Central platform for running the algorithms upon the TVS data. So just a brief reminder of the data. We recruited participants from each of the congestive heart failure, COPD, healthy adult, multiple sclerosis, Parkinson's disease, and proximal femoral fracture cohorts. Participants were assessed over a range of tasks conducted in laboratory environment, where mobility was measured from a single McRoberts device and a 3D motion capture system, which served as our gold standard reference. They also completed 2.5 hours of free living assessment in their home and surrounding environments, and mobility was measured again with the McRoberts sensor alongside the INDIP system, which served as our free living gold standard reference. In short, the algorithms were run on the IMU data that was obtained from each cohort in each condition, and then compared to each other based upon their performance relative to the gold standard. The TVS protocol and equipment, along with the process of identifying which algorithms were analyzed in the TVS, have been extensively covered in papers and previous webinars. So the large number of identified algorithms underwent development and optimization in accordance with definitions agreed by the consortium and coded in software packages such as MATLAB and Python. Each algorithm was then uploaded onto the secure Mobilise GitLab repository for storage, which also easily allowed algorithm developers to access the code. The algorithms underwent many iterations of development, representing excellent teamwork and communication between the algorithm developers. Moving towards eScience, we needed to ensure that the code written in MATLAB or Python was able to run harmoniously with each other. So we adopted an approach utilizing Docker containers. As Hugo has already explained, in essence, every algorithm written in either MATLAB or Python was packaged into its own separate block to enable it to be selected and run on the eScience Central platform. The block enables the code to run in its own separated environment and be combined in the same workflow with algorithms from other languages. And a practical example would help make this a bit clear in a few slides' time. Once all the algorithms have been packaged, they are ready to be executed within workflows on the platform. Hugo again has already provided an overview of the platform along with some technical descriptions of some of the functions of the workflow blocks. However, here I will provide a practical example of how we ran the Cadence algorithms upon the TVS dataset, utilizing eScience workflows in the context of the healthy adult cohort. So first, we created our driver workflow, which can iteratively run all Cadence algorithms for a single participant of the healthy adult cohort with a single click. The first block within this pipeline loads all of the healthy adult cohort data that was collected from each of the 4 sites. The next block of the driver will activate the Cadence workflow to run iteratively for each of the 20 participants within the cohort. The Cadence workflow actually contains and processes all the data with all of the Cadence algorithms. But what's actually happening within these Cadence workflows? Well, looking within the Cadence workflow, the first step is the pre-process block that runs functions relating to extracting time zone and naming information. When dealing with the large number of participants, this step is crucial in being able to distinguish which Cadence results belongs to which participant. Next, we apply our dummy algorithms, and these algorithms use fake or dummy outputs coming from the gold standard in each condition to allow independent assessment of each of the subsequent blocks. So first up is dummy gate sequence detection, then dummy step detection, then dummy left-right detection. And then we can apply our Cadence estimation algorithm upon the output received from the dummy blocks. Within this block, we can select any of the 20 Cadence algorithms which were packaged within the Docker containers from GitLab. So our single Cadence workflow now contains all 20 Cadence algorithms, although for graphical representation, this is an example of just 6 here. The output of each of the Cadence blocks is then stored in a data.map file in the output, as you can see here. Then after we've estimated Cadence, we now have the stride interpolation block, which ensures that the output of Cadence is defined on a per second and per stride level. And then this creates Excel documents for the per second cadence and the interpolated per stride cadence. Then we have the post-process block, which ensures that the file is named after all of the blocks that it has been processed by, so that the researcher can distinguish the participant, algorithm, and context from each other. So just for an indication of the file volume, each of the 20 Cadence algorithms has 3 output files, as you can see here. So there are 20 algorithms with 3 files each. Therefore, there are 20 participants. So each participant has 60 files in one context, either laboratory or free living. That means that there are 1,200 files per context. Each cohort has 2,400 files. So once all the Cadence algorithms have been completed for all participants, it's back to that driver workflow. The driver will then collect all of the individual files before saving them inside the same folder to enable easy access for download. As mentioned, this is repeated separately for free living and lab-based data, and eScience Central makes this entire process straightforward and efficient, as an entire cohort's data can essentially be processed with a single click. So you're probably wondering now how quick this whole process takes. Well, it does depend on the size of the data, as understandably, the 2.5 hours free living data is much larger. And it also depends upon which block of the algorithms from the pipeline are being processed. In a complete run of an entire cohort for Cadence in free living, this will probably take 2 to 3 hours. Lab-based is usually an hour at most, so naturally we repeat this process 5 times for each cohort It's roughly around 20 hours of processing time. Stride length estimation was the longest block, as it included machine learning models, which included in just some of the algorithms, and this took exceptionally longer, almost 168 hours of processing time. So the results are stored within the folder created by the driver, which is run on a specific cohort, on either lab or free living assessment, which is then stored on eScience. So here we employ the file manager tool, where I select the driver folder which corresponds to this data, before the tool downloads the data onto the local drive in our specific folder format. This process is then repeated for all cohorts and all assessments. And once we have the data for a given cohort across both lab and free living results, a quality check is implemented to ensure that we have a complete data set and resolve any errors that might have occurred in execution of the code. So once we have all the data is downloaded from eScience, it's then ready to implement the statistical analysis plan and find the best performing algorithms.
Hi, I'm Luca Palmerini. I'm a researcher from the University of Bologna in Italy, and my main role in Mobilise was to develop and implement a procedure of data standardization. So what data are we talking about? So first, the data that are needed to estimate digital mobility outcomes, such as real-world walking speed, from inertial measurement units, so wearable sensors. So these data are accelerations, angular velocities, and so on. If you want to know more about this, you can watch webinar number 1. Then there are data that are needed to validate these digital mobility outcomes. So data from the gold standard. In Mobilise, we have the stereophotogrammetric systems in the laboratory sessions. And for these systems, we have both the raw data, so the marker data, and the related process outcomes that are needed to validate the extracted digital mobility outcome. Then, in the free living sessions, we have the INDIP system, which is made of multiple inertial measurement units, pressure insoles, and distance sensors. Also here, we have both the raw data and the process outcome. If you want to know more about these systems, you can watch webinar number 2. So these data are in Mobilise, but we actually started before with datasets from the consortium partners that were already available when Mobilise started. And algorithm implementation and validation started on these datasets, but there was a related challenge, as datasets were collected from different partners, and different research groups used the sensors with different characteristics, gold standards with different characteristics, different synchronization procedures, different software for analysis, different procedures for many topics. There was limited data publicly shared or already structured for sharing. And in general, we found that there is no universally accepted strategy for data standardization, formatting, integration, organization. And this makes it difficult to reuse or combine data. So we standardized these datasets so that algorithm developers could use one or another dataset in the same way, regardless of their specific characteristics. And this standardization procedure made it possible to process pre-existing datasets and mobilized datasets in the same manner. It made the quality check easier, and we believe it made life easier for algorithm developers, so for the one developing algorithms to estimate digital mobility outcomes, but also for future researchers assessing the data. So we identified 5 main topics for standardization. So the data structure and file format, the sensor locations and orientation conventions, the measurement units, the timing references, and gold standard. So regarding the data structure and file format, we had a single folder for each subject, and for each subject we have different folders for their recording sessions, so laboratory, free living, and 7-day monitoring in Mobilise. And each of these folders contain a MATLAB file, data.mat, which contains the main information, so the accelerations, angular velocities, and so on, and a support file, info4algo.mat, which is a file that is information for algorithm developers. So it contains information such as the presence of a mobility aid during the recorded test or the subject A. We implemented a different organization depending on whether the setting was structured, such in the laboratory sessions, or unstructured, such as in pre-living and 7-day monitoring. This allowed the flexibility, and for example, it allowed in the laboratory session to store different tests, such as the time up and go, sit to stand, the walking test, and for each of these tests, different trials related to it. So, for example, different repetitions of a time up and go. Then we have a structure for data from sensor units and a structure from data from gold standard. So regarding sensor data, we have the sensor position, and then we have all the signals recorded, so acceleration, angular velocities, and so on. The related timestamps and sampling frequency. This is a structure that it is easily generalizable for a different number of sensor units and a different number of positioning of the sensors. We developed a general orientation convention based on the anteroposterior, vertical, and middle-lateral directions, which can be used for different positioning of the sensor in the body. We also implemented a procedure for standardization of data from the gold standards, and I have to thank Tecla Bonci and Francesca Salis for their help in this. This structure allowed for flexibility, so to store data from different gold standards, so photogrammetric system, in-depth, but also, for example, instrumented walkway that were present in pre-existing dataset. It allowed to store both raw and processed data, and it allowed for management of missing values and technical problems such as marker occlusion. So what do we think are the pros of this procedure? Well, processing of data with a standardized format is easier regardless of the origin. The structure is flexible. It is sensor and gold standard agnostic, so it doesn't depend on a specific sensor or gold standard. It allows an easier check for possible problems for low quality data. And it allows the fast implementation and validation of algorithms, also using previous datasets, such as in this publication from Soltani et al., where two different pre-existing datasets were processed and used. So what we believe that this procedure will be useful for? Well, it will be useful for an easier data sharing, to allow researchers to understand the data that will be available for Mobilise. And also this will provide researcher a standardization procedure that can be used to format similar data. But there are some related limitations. While some choices were specific to Mobilise and previous partner expertise, such as the choice of MATLAB. There was not enough time for full consensus, and some modifications and adjustments were made on the go. For the future, we believe this standardization work can start a discussion or consensus towards an accepted standard for several aspects of data recorded from wearable sensors. This standardization procedure will be available in an article which is currently under review in Scientific Data. And to understand where and when it will be possible to access standardized Mobilise data, you can see Brian Cofield's next presentation. I would like to acknowledge the big work from my two colleagues, Luca Reggi and Ilaria Dascagno, in this standardization procedure development. and the whole WP2 team of Mobilise. So thanks for the attention, and I leave the stage to Brian Caulfield, who will talk to you about Mobilise data sharing. Thank you.
Thank you very much, Luca. And now I'd like to spend just a few minutes talking about data sharing and Mobilise-D. It's very clear that Mobilise-D is a very large program of research, and over the course of the 5 years of the program, we are going to generate quite a lot of data. We've already generated a lot of data. And if you go to our website and look at the pages that are dealing with the data set that we are generating, you'll see that there's quite a diverse range of data that are involved in the program. We have data from large comprehensive systematic reviews that have been carried out. We have a lot of qualitative data and transcripts of interviews that have been carried out with patients and with clinical experts and domain experts in the various areas that contribute to the program. We have a lot of data, sensor data from a young adult population, which has been used as reference data for the technical validation study. And then we have the two main programs of work with the technical validation study itself, where we have a lot of data, multimodal data from laboratory and in-home and wider home and community environments. And we have the large clinical validation study data set, which incorporates data from over 2,400 participants who are being monitored over 5 different time points over 2 years. Just a quick kind of order of magnitude in the clinical validation study data set, we are expecting that we will have over 1.3 million hours of inertial sensor data from the lumbar spine of people as they wear it in their daily lives. So quite significant data involved in the program. And always when we're generating such a large data set with a large contribution of the funding coming from the public purse, the most obvious question is, will you share your data? And I think the very clear and simple answer that we want to give is that the answer is going to be yes. We have published on our website our commitment to data sharing, and we do plan to make our data available to the wider community after collection and processing has been completed, and subject to all of the normal and usual ethical and data privacy requirements being met. But in making our data available and in making this commitment to open data, we also need to balance some other considerations, and amongst them the needs of the academic partners who are carrying out the work of Mobilise-D, and as well as that the needs and in recognition of the very significant financial and time investment of the different EFPIA partners who are contributing to the Mobilise-D program. And it's when all of these are taken into account that will help us to deliver the detail on how and when we will and where we will actually make our data available. So very simply, this is an overview or an extract from our data sharing policy that is in final stages of preparation and will soon be published on our website. We will be making data available when it has been collected, has gone through the appropriate quality checking, analysis and curation processes, when it has been utilized by members of the consortium in respective peer-reviewed publications that support the objectives of the program, when the consortium, including the academic and EFPIA partners, have agreed to the terms and conditions for the use of the data and have agreed to its release, and also when the person who is requesting, or when the entity who is requesting the data has agreed to the terms and conditions of use. How we will share the data is the next question that often will come up in conversation. And we have two main pathways towards sharing data in Mobilise-D. In many cases, the data will be made available on an open data repository where there will be a self-serve model, and members of the scientific community will be able to access and download the data as they wish, so long as they accept the terms and conditions of the license of use that is going along with the data. And I'll come back to that in a minute. We also plan to make other data available through our own Mobilise platform, our own portal, with more of a controlled access model where there will need to be a specific request made for the data and an acceptance of terms and conditions for release of the data. The details around exactly how that will occur are still being worked on, and we will release them in a short time. And just before I finish, I want to say that, you know, the good news is that we have already shared quite a lot of data. You know, there's a combination of software assets, processing code, algorithms, questionnaires, data from questionnaires, some samples of sensor data, inertial sensor data, as well as a large range of data that have been extracted from systematic reviews have already been shared. You can find some details of some of these on our website, and we're adding more as we go on. I'm happy to say that I did a quick look at this morning, and to date we have had over 175 separate downloads of data sets that have been made available, or assets that have been made available by the Mobilise consortium. So this is already underway. So it's just a very brief overview, and now I'd like to pass you over to Sylvia.
I'm Dr. Sylvia Delding, and together with Sarah Koch, we're going to explain and present the Technical Validation Study Statistical Analysis Plan. Also, many thanks to Anneli Carsen, who helped us for the slides and the presentation. So again, a little bit of semantic. We need to understand what we mean with technical validation. So with technical validation, we're really going to test the criterion of phase validity, and in the specific, the concurrent validity of our sensor. What is concurrent validity? It's the extent to which the new instrument relates to another measure of the same construct that is measured in the same subject. So am I quantifying what I want to measure correctly? And how we can do that? We can do that, obviously, we need to do that using a reference system, a gold standard that can be and has been used, for example, in the lab. And with Mobilise, we have the possibility also of validating and so quantifying concurrent validity and technical validity in real world conditions. So just again, a quick hint at the objective of the technical validation study. The objective of the technical validation study is to conduct a technical validation, so test technical validity of a device and algorithm combination capable of quantifying walking speed, which is our primary DMO, and other digital mobility outcomes. Criterion validity, as shown you before, will be evaluated comparing these DMOs to those evaluated by a reference system in 5 different clinical cohorts and in healthy adults. And again, just a quick reminder of the technical validation study protocol and the data that we're going to use. So the technical validation study has collected data in 6 different cohorts: proximal femoral fracture, COPD, chronic obstructive pulmonary disease, congestive heart failure, multiple sclerosis, Parkinson's disease, and healthy adults. And as you have seen in the last webinar session, the protocol was quite an extensive one. And the data that we're really going to focus for the technical validation analysis are the in-lab assessment and the 2.5 free living real-world assessment. So what are our reference systems against which we're going to validate our single sensor? So in lab, we are using the microbial Dynaport, so the single sensor, and the INDIP system. And we're going to both compare them against a gold standard, which is a stereophotogrammetric system. So for the sensor, it's going to be a real validation. For the INDIP system, it's going to be a check of the performance of the INDIP system. For the 2.5 hour, for the free living assessment, we're going to again use as a reference system the INDIP system, and we're going to again check the performances of the DMOs evaluated with a single sensor versus the INDIP. In the 2.5 hours, we're going to also utilize some contextual factor data that, as you've seen again in the previous webinar series, we're going to quantify through the Equora app and Beacon. So what are the outcomes that we're going to focus? The quantification of digital mobility outcomes, as I say, it's using a single sensor as one algorithm. And again, as I've seen in the first webinar series, the algorithm is quite a complex process that collects IMU data and through a variety of blocks gives our digital mobility outcomes. So the digital mobility outcomes are going to focus are the primary outcome, which is the walking speed, and a set of secondary outcomes. As you can see here, are walking bout duration, stride and step duration, cadence, stride length, turns, stance, and swing space duration. As I said before, we're going to also utilize some contextual factor to help us identifying and better describe the validity using indoor and outdoor information that we get from the EQRA app, and using the information whether someone is using a walking aid that we can derive from the utilization of the beacon. And now I'm going to give the presentation to Dr. Sarah Koch, who is actually going to explain the statistical analysis plans more in depth.
Hello, my name is Sarah Koch, and I'm a postdoctoral researcher at the Barcelona Institute for Global Health. I'm here today to talk to you about the statistical analysis plan that we put together for the technical validation study, or the TVS, within Mobilise-D. Right at the beginning of Mobilise-D, we put together a team of experts consisting of statisticians, epidemiologists, algorithm experts, and big data scientists to write the statistical analysis plan with the purpose of clearly describing the purpose of the technical validation study, of also describing the data collection procedures and the actual data and variables that we were going to collect. And lastly, to put together a document where anybody who would join the consortium at a later time point could find a clear outline of all the analyses and statistical procedures that were proposed to do to analyze the data collected within the TVS. As you can see here, this was a true team effort, and a lot of hours went into this to put together a document that then ended up being over 80 pages long. One of the challenges within this writing process of the SAP was to find a common language. Quite often, we noticed that people were familiar with the terminology, but that depending on the discipline someone was coming from, same words could mean different things. So first, a consensus had to be found in a common definition of a term, such as predictive capacity, to then move forward together and put this SAP together. What you can see here is that to analyze the DMOs, we distinguish between three approaches. We use performance metrics, criterion validity metrics, and different plots to visualize the data. Let's look first at the performance metrics that we use. Here, we distinguish between sensitivity analysis, positive predictive values, accuracy, specificity, and F1 score. Then, to look deeper into criterion validity, we use absolute and relative errors. We calculate maximum and root mean squares of absolute errors. We calculate the Cohen's kappa, and we report the ICCs to look at concurrent validity. And of course, we also report the p-values that come with them. Then to visualize the data, we use Bland-Altman plots, scatter plots, and histograms. Here you see a more in-depth sort of overview of how we analyze the DMOs. So what we did is we went one by one through each DMO and looked at its specific structure to then determine which type of metric makes the most sense for that specific DMO. When you look, for example, of walking speed or any of the DMOs that are highlighted here in light green, you can see that we use the criterion validity metrics to analyze them. So for walking speed, for example, we calculate absolute and relative errors. We calculate ICCs and report the p-values that go with them. And we use all three plot types to visualize the data. This type of DMO, so walking speed, is a different type of DMO from the ones that you can see in brown or dark orange that identify or characterize a start or an end time of something, such as the start or the end of a walking bout or the start or the end of a turn. Here you can see we cannot calculate ICCs for them, and therefore we rely on reporting absolute and relative errors, and we use histograms to visualize what's going on within these types of DMOs. What I'd like to show you here with this slide is that we essentially analyze our DMOs on three levels. We use the walking bout level as the smallest unit of analysis. Then we analyze them on the subject level and the cohort level. And with that, I hand it back to Sylvia. Thank you very much.
Thank you very much, Sarah. She's explained the sub very well. And now I'm going to dig into, obviously, our unit of measure that, as Sarah just described, is a walking bout. So again, just a reminder that of something that we've seen before in the previous webinars. What do we consider here a word walking? So what is a walking bout? And as Felix has presented in the first webinar, a walking bout for us is a walking sequence containing at least 2 consecutive strides from both feet. We know that start and the end of the walking bout are determined by a resting period or any other activity. And within a walking bout, we have specific criteria on, for example, stride length and stride time that allow us to identify specific or eliminate a specific stride within a walking bout. Once we do that, we have the possibility within each walking bout to extract and quantify our digital mobility outcomes, as I've shown you before. So I'm going to just get you through a working example of, if you want, the identification of walking bouts and how we do quantify the statistical analysis plan metrics that Sarah showed you before. So how do we identify a walking bout and which are the performance metrics that we are utilizing? So for the identification of a walking bout, we use the whole signal of whether it's an in-lab assessment or a 2.5-hour assessment. And we use a sample by sample strategy. So we're going to have, for example, a walking bout that are identified by the single sensor. As you can see here, we've got like 4 walking bouts. And in white, you can see a sample that is identified as a non-walking. And in gray, instead, a sample that is identified as a walking. And then we're going to have the same, obviously, a walking bout identified by the reference system. In this case, again, 4 walking bouts. For each of the sample, we're going to identify the true positives. So walking bouts or samples that are correctly identified by the single sensor as walking. We're going to then identify false positives. So those samples that are identified as walking by the single sensor, but that in reality are not walking as per reference system. False negative, so single sensor is missing, if you want, a walking here. So single sensor is incorrectly identifies something that is not walking when indeed the reference system is identified that as walking. And then the true negative, when both the systems, so single sensor reference system, are really identify something that is not walking. The performance metric that we are then deriving from true positive, false negative, and true negative are the sort of classical ones. So we're going to look at sensitivity, specificity, accuracy, positive predictive value, and F1 score. This will give us a really, I would say, 360-degree idea of how well our algorithms work. So in this case, for example, again, we have an example of a performance. And in this case, we're going to have, for example, a sensitivity of 0.5, specificity of 0.6, accuracy, positive predictive value, and F1 score. When we have a walking bout, obviously, we're going to then identify, for example, one of the DMOs that I've shown you before is walking bout duration. How do we do that? Again, we're going to have walking bout that are identified by the reference system and walking bout that are identified by the single sensor. And we're going to have a duration for each and one of those. Of course, within this specific example, we're going to have a walking bout that, again, can be a false negative, so something that is not detected by the single sensor. We're going to have true positive walking bout, so walking bout that are detected both by the reference system and the single sensor. And we're going to have false positive, so walking bout that are detected by the single sensor as walking, but that in reality are not. So the Criterion validity metrics that Sarah showed you before, we're going to use a couple of different strategies to actually identify this analysis. The first type of analysis we're going to base on all identified walking bouts. So for the reference system, we're going to utilize all the 3 walking bouts detected by the reference system, and by the single sensor, again, all the 3 walking bouts that are identified by the single sensor, whether the walking bouts are true positive, false positive, or false negative. So we're going to be able to have these results at the participant level, okay? Whilst the second type of analysis are going to be based on the true positive walking bouts. So some type of analysis, for example, ICC or THS, are actually needing to have a 1-to-1 correspondence between the walking bout of the single sensor and the reference. So for this type of analysis, we're going to be able to focus on only the true positive walking bout. Hence, we're going to have some results or performance metrics at a walking bout level. So in this case, for example, just an example of Criterion validity metrics, if we look at an absolute error, In the first case, for the results at the participant level, when we do include all identified walking bouts, we're going to have an absolute error that is evaluated by looking at the mean duration of all over the walking bouts for a single sensor, minus, for example, the mean duration over all the walking bouts detected by the reference. For the results of the walking bout level, instead we're going to have an absolute error that it's possible to evaluate for each true positive walking bout. In this case, for example, we're going to have 3 different walking bout duration for the single sensor, 3 different bout duration for the reference system. We're going to average mean walking bout duration for each of the 2 systems, and we're going to have an absolute error per participant, if you want, considering all the walking bouts identified. In the second example, we're going to have an absolute error that, in fact, we're able to evaluate for each walking bout. So we're going to have an absolute error for walking bout 1, the true positive, and walking bout 2. Another thing that we're going to do is, obviously, we're going to have bouts of different lengths. So we're going to look at a weighted error in this case as a working example. In this case, we're going to have, for example, a variety of duration from 7 seconds to 2.5 seconds, okay? And we're going to evaluate a weight by looking at the proportion of the length of the walking bout divided by the total length of the total walking bout. So in this case, as you can see here, we're going to have different weights for the different walking bout length. And the weighted mean error is going to be, again, the average of the error that we identify for each walking bout that is weighted, so multiplied by this weight. We're going to give, to some extent, more weight to the longer walking bout and less weight to the errors that are coming from the shorter walking bout. Again, in terms of plots, Sarah has shown you before that we're going to provide scatter plots and blind number plots. And in this case, obviously, we're going to look at, if you want, the values that are derived from the reference system and derived from the single sensor. In this case, we have to have one-to-one values, so we only can present these type of plots for the true positive walking bouts. So in this case, we're going to have walking bout duration of the reference system on the x-axis and walking bout duration of the single sensor on the y-axis, and we can then derive R and linear regression. For the blind number plots, we can derive obviously the limits of agreement, and we can also check the bias, so the mean difference between the two systems. In this case, on the x-axis, we're going to have the mean between the single sensor and reference system, and on the y-axis, we're going to have the difference between the reference system and single sensor values. In this case, we can also code to some extent each walking bout using other characteristics of the walking bouts. For example, we can look at the walking speed. So for each walking bout will be colored by the walking speed that is related to it, and see whether errors, for example, or correlation are affected by it. We're also going to look at some supplementary analysis. We're going to look, first of all, of the effect of walking bout length on the results. As we know, when walking, we can have a variety of walking bouts that have different lengths. So we're going to look at specific thresholds, for example, walking bouts that are very short and they might be more challenging and more noisy. So less than 10 seconds, 10 to 30, 30 to 60, and 60 seconds. And we're going to look at the algorithm performance against the reference system, looking at, for example, how this can change depending on the walking bout duration. And we might see that obviously errors might be higher for very short walking bouts and so forth. We're also going to look at the effect of contextual factors on our results. So we're going to look at walking bouts, for example, that are detected as being indoor versus the walking bouts that are detected as being outdoor, and looking at the performance metrics in these specific scenarios. And we're going to also look at the same, looking at with and without walking aid. So walking bouts that are detected as being sort of carried out with the use of walking aid and not. So we can see how our performances of our algorithms are actually changing depending on these contextual factors. Obviously, there's going to be a lot of work. There's going to be a lot of walking bouts that we're going to look at. And I'm just going to ask the audience, how many walking bouts across all cohorts and assessment do you think we're going to be looking at? It's going to be 3,000 walking bouts. So how can we really be able to visualize and making sense of all this data? It's a bit of a spoiler alert for the next webinar session, but thanks to Dr. Alma Cantu visualization tool, we will be able to really look at individual walking bout and select and see correlation plot, blind number plots, and really perform a data exploration using this fantastic sort of visualization tool. Thank you very much.